Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing, lecture number 60, and the topic is basically sensing the qubit, the microwave technique. So, in our previous lecture, which is lecture number 59, we were more concentrated on the last part of it, at least on the optical method of detection of the spin qubit state. In this case, we will be studying more on the sensing of the microwave technique of sensing of the qubits. So, we will look into the principle of microwave qubit sensing, we will look into experimental techniques available, we will look into single shot spin qubit, and within which we will look into voltage pulse sequence, and then quantum point contact signals and energy level diagrams related to contact point signals. Now, the principle of microwave qubit sensing, so what you do is that you apply microwave pulse or applied a pulse to the qubit resonance frequency. So, let us say I have a resonant frequency of x1, then the radiation, when it falls at x1, you do have a large amount of energy transfer taking place. Now, and that is what, if you have state 0 or state 1 of the system available with you, then it changes the cavity resonance condition. Depending upon the state which you are, it changes the cavity resonance condition. So, what you do, the measurements are done by the incident or the transmitted microwave signal. So, what you do is you send the microwave signal inside the spin qubit, it gets reflected back. Once it gets reflected back, you can look at its parameter and do a prediction about the state of the spin in the qubits, right. And the advantage is that unlike the previous one, here it is scalable to many qubits which you do. Okay. Now, let us look at this particular diagram here. So, this is a reservoir of large electron. I have a dot here, quantum dot with a spin up state. Obviously, let us suppose there is a filtering and the spin up state is not allowed to go into reservoir. With spin down state, there is a sudden change in the reservoir, and what happens is my electron current, which was negative, now it suddenly increases, the q dot increases and then remains stable. So, this is basically a charge, spin to charge. What you are doing is this particular type of spin is being converted to a charge, and depending upon the number of spin up qubits, your charge will change, right. So, this is the basic concept of spin to charge conversion schematic in this case. Now, you understand this particular point, that these quantum dots are primarily those which are spin qubits. They are generally superconducting qubits at very low temperature, ultra low temperatures. But when you talk of quantum dots, which are generally calculated by using a heterostructure, which is basically, if we talk of 3-5 semiconductor, there are buffer layers and there are active layers available, and they are sandwiched to generate a large 2-dimensional electron gas. From there, you can actually generate some quantum dots by generating a quantum well. Depending upon the nature of the spin, you can actually have either a spin up or spin down. Let us suppose I have a filtering for spin down, then I will have a large transfer of spin down, which results in a larger amount of charge and therefore a current. Now, the key idea behind this is that whether charge leaves the dot or not, one can infer the spin state of the kin. So, it is something like this, that if you have the state of the qubit is known to me, and if I have a filter which predicts a transfer of qubit because of the filter, then you will see automatically the charge on the right hand side of the filter, from where the filter is being extracting the information, will have large value. Say for example, let us say you can say that this is called spin to charge conversion. That means that let us suppose spin is of one state and the filter does not allow you to move that state outside, the charge remains constant. Whereas, when the flipping takes place, the charge changes and the electron tunnels out. When the electron tunnels out, you suddenly have a shoot up in the current which is available to you. That is the key idea for any microwave qubit sensing, right. Now, let us take up the first part, and that is spin up. Let us suppose a single electron with spin up is, let us say, is confined in the quantum dot, right. It is confined in the quantum dot, let us suppose. This one is contained at and the energy of this state lies below the Fermi level. As it lies below the Fermi level, the electrons cannot tunnel out because there is a large hump to overcome for the electron to move away. Therefore, the charge on the q dot remains constant at E, which is, you can see this one. Now, and therefore, q dot stays flat at minus e with respect to time. So, as the time even proceeds forward, since you are not changing the energy of the electron, you are not actually allowing it to move above the Fermi level, or you are not allowing even to do a tunneling of the charge carriers. As a result, the state of the electron and the number of electrons remains almost constant with respect to time. Whereas, in the second case, which I will do in the maybe in the next case, yes. Now, with a spin down, let us suppose, which is the second graph, this one, right, spin down. If the energy level is positioned above the reservoir level, Fermi level, the electron can tunnel out of it. So, let me say the concept is that I have the reservoir Fermi level is here and my queen spin state is here, then I can easily allow it to move it to a lower range, and therefore, the electrons can tunnel out and in of the reservoir very easily. And as it tunnels out, the dot becomes empty, and therefore, the charge state goes from minus e to 0, and therefore, you see a step change happening at this particular time t, when it goes from minus e to 0 charge q dot here, right, and this has been taken from this source which you can see at the end of the slides in a sense. So, basically the concept therefore is that you try to engage the electrons such that its energy above the reservoir Fermi level. If it is below the reservoir Fermi level, obviously you will not have any tunneling happening. If it is above it energy level, then it can easily tunnel through and come, not tunnel through, it can just ride over to the reservoir, and when it rides over to the reservoir, the state itself becomes devoid of any electron, and therefore, the electron state goes from minus e to 0, assuming there is a one electron state available within the quantum dot. So, this is the basic principle of the, as you can understand, when you have a top spin, this does not allow you, and therefore, electron remains within the state, confined to the state, and therefore, it is constant with respect to time in that case. Now, let us look at an experimental technique. There are available experimental techniques which are there with us, and what we do is that we try to do what is known as a coupling qubits to the microwave resonator, and we use a quantum point contact QPC for detection of charge detection. This shows the micrograph of quantum QPC and gates, right. So, the QPC and gates are available to me. IQPC is basically the current which is flowing at this particular point. I have a source here, I have a drain here, right. This is basically the reservoir, this part is reservoir, right, and this R value I can show you in the next slide maybe, right. If you look at this component, these are the quantum dot is basically, this one is the quantum dot which is placed here. This is the experimental data I am showing you. This is the quantum dot, let me write down here. This is the QD, the quantum dot which is shown here. They are formed by applying negative potential to T, M, P and R, which means that you apply negative potential here, 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 and then what it does is that it tries to confine, because when you put a negative potential, it forms a well, quantum well, and all the electrons are all residing inside the quantum well, right, and therefore, they form a well, right, and that is what I have written, that it acts as a box and which traps a single electrons within the box itself. Now, the tunneling probability or the tunneling coupling to the reservoir, this is the reservoir which I have told you, and this side is the IQPC current through the QPC, quantum point contact. Now, the tunnel coupling to the reservoir is controlled by the gate voltage, right, it is controlled by the gate voltages, and if you have reservoir, it provides or accepts electrons via tunneling. So, reservoir is basically a large electron reservoir, and it accepts, or it can also not only accept, it can also give back electrons there. Obviously, the tunneling rate tau is basically tunable. I can tune the tunnel rate to favor my process conditions. So, I have a reservoir, I have a cell here which quantum confinement is done here, the quantum dots are inside the white circle which you see here, and this is the reservoir which takes care of the tunneling of electron from the reservoir onto the tunneling back and forth. It can go back and forth both ways depending upon the potential given to M, T, P and R. Now, you have obviously a narrow conducting path which is available to us next to the dot. So, I have a dot here, and just next to the dot you have the quantum path available, and this serves as charge detector. So, when the electron tunnels into or outside the dot, it obviously changes the electrostatic potential and therefore, it modifies the IQPC. So, final value of the current is basically looked at IQPC, which is here with this part, and this tunnels in and out. Now, when it goes out, it is basically further away from IQPC. As it tunnels inside, it increases the value of IQPC. So, basically the placement of the quantum dot and its spin in a sense calculates or corroborates IQPC, the quantum point contact current which is providing, and this is one of the methodology by which we actually see whether a current is flowing or not. You need to also provide a voltage source at P, which we will be looking afterwards, but we also need to provide a magnetic field parallel to the two dimensional electron gas 2DEG. The 2DEG is this one, and you need to provide, this is my 2DEG here, this is my 2DEG, and you need to provide magnetic field parallel to the plane of 2DEG. So, what you do, so if this is the plane of the quantum dot which you have kept, you apply a magnetic field in this much, and this splits the electron spin states top and bottom, known as Zeeman effect. So, it is something like this. If you have mixed salt and sugar, and if you want to extract only the sugar outside, then one of the methods to do it is that you separate salt and sugar using some technique, and then you try to take out the sugar individually. Exactly the same here, you apply a magnetic field. Because of Zeeman effect, the magnetic field will tend to split the spin states which are positive and negative in energy level, and then it will allow you to do a spin selective readout in the output. That is the advantage of having this Zeeman effect, helps you to do that at least, right. So, the magnetic field is applicable to the two dimensional electron gas. Now, if you look at this procedure for single shot spin qubit readout, all our discussion is on single shot spin qubit readout. The procedure is that you have an empty dot, right, empty quantum dot available. You inject a single electron and then you measure the spin. Spin state and the charge state are then correlated with respect to each other. Now, the spin will remain at top or bottom. If it is bottom, it tunnels out, and this can be detected via QPC current. So, the whole flow which you can see is basically is you have an empty dot. Empty dot primarily means that your potential is suppose 0 and your del IQPC is almost 0. Then what you do? You insert, you increase your Vp, you inject the single electron here, and then you wait till T wait, because you have to give some time for the injection to occur and stability to occur. After that, you go for readout, right. In this case, for example, when you inject and wait, your current actually suddenly shoots up, because you have injected a type of spin qubit onto the system, and therefore, suddenly the current will rise up, and that is the reason you see Vp, which is the applied potential at particular point, rises up, right. So, you see, so these are all related to each other, these diagrams. So, initially it was empty, you see they were, this is the Fermi level, they are empty and they are very far from each other. Then you apply a pulse, and when you apply a pulse, suddenly your bottom and top are basically separated by an energy level by the Zeeman effect. Then you allow it for readout. When you read out, then there is output and input currents are available to me, and then finally again you reach the empty state. So, what you do is that you empty, this is the place where you inject the spin, this is the where you do the readout by doing del IQPC change, and then finally you go to empty. If you see here very closely, the left hand side is basically the Fermi level, this is my EF, and this is the state of the spin qubit within the system. Whereas this one is again, you come back to the original state when it is empty, and what you have done effectively is that you have spin up state have been converted back into the system as such, right. This is basically known as a 2-level pulse technique for spin qubit. So, I am assuming that by applying a magnetic field, I have been able to split the electrons in up and down, and I have been able to segregate them properly, and then what I do a readout. After readout, I go to empty. One needs to ensure that there will be latency will be high, provided your inject and wait time or T wait is much larger. Similarly, you have to give some readout time, right. and so the total time from inject to at end of readout will be the total amount of time before any new state is detected in reality, and this is methodology known as single shot spin qubit methodology. Again I will discuss this point in detail. There are 3 stages: empty stage, the first one is the empty stage, the dot is empty, no electron is inside, right, and therefore Vp is almost 0. A single electron with random spin top or bottom is injected and this tunnels into the dot. So, suddenly the charge in the dot increases and therefore Vp also increases, and you suddenly see a increase in the value of the voltage here, right, and then it remains there for t wait here till a particular time, and then what I do is that at certain point of time I do a readout. Readout is basically, readout stage is basically the energy levels are tuned so that, say for example, down state negatively aligned states can leave, but positively aligned states which are up in states stays there, right. So, when the positive state or the tops up spin state goes away, they are read using an IPQC, and then again you come back to the empty state. So, this is the procedure which you adopt here, right, and this is one of the so this is basically a voltage pulse sequence in the input side where you should give Vp value such that they go from empty, inject and wait, readout. So, let me show you maybe here. Yes, this is the point where I am giving the injection, where I am injecting it. So, this I give this, it comes like this, and then again I go like this. So, this state is read, this is inject and wait, read, empty. So, this is empty. So, I am giving this pulse from this sort of, from this point, and this electrode helps me to ensure that the state of the electrons are well fixed and predetermined, and there is a spin to charge conversion taking place. Okay. Now, let me come to del IQPC variations. We have looked into Vp variations, we will now look into del IQPC, quantum point of contact signal, right. Now, if you look at the QPC, how it changes with the charge state of the dot. So, understand, when there was no charge in the dot, obviously your Vp was almost equals to 0, your del IQC will be almost equals to 0, and that is the reason it is almost equal to 0, which you see here, this part. Now, if you look at step, this is where you inject the charge carriers, and therefore del IQPC also increases. Now, this is the point where you insert the system, as I discussed with you, that if you go back to our previous slide, let me show, yes, you see this. So, this is the point where you suddenly see a rise in the charge. Just look at this, the reason we have already discussed, and compare that with this one, that because of that the current suddenly falls down to a new value, right, and it remains that like q dot equals to minus E is available to you, and then we come to the out state. So, step downwards when an electron enters the dot, this is q dot equals to minus E. So, I did what, I pushed an electron, a negative charge comes to the dot, the current falls down and it remains in this state, right. Now, when you do a readout, this is the readout state, readout stage, if a step is detected, right, it indicates a negative spin, and if a step is not detected, then we define that to be as a positive spin or a top spin, which means that this dotted curve which you see here, right, during the readout stage, if a step is detected, which means that I have a small step available to me, it indicates that down spins have been activated. If no step occurs and you go like this, then we say that the spin high always remain the same, and you can understand why, because when you change the state of the spin, the current will obviously change, right, and that is the reason you will see that the current shows a sharp shoot in the when you have spin down state available with you, and this implies that the current has tunneled out, the charge carriers have tunneled out, and therefore the current has suddenly increased. That what you see here in this case. If there are no step in occurring, then of course you will say that there is no tunneling out of the carriers, because the number of charges still remaining the same. Then you go back to again q dot equals to 0. However, these are the order of few microampere current changes which you see. So, your readout circuitry also should have equipments or devices which can read very small currents in a sense. So, this was the basic idea of a QPC diagram. Let us look at the energy level diagrams, which is the third part of it. And what we did was, the energy level relative to the reservoir, which is the Fermi level, has been shown here, right. So, what we do is that we inject, let us suppose first diagram, which is injection, we have waiting, then we have readout, and then we are emptying, and then we again go by the same process of injection, waiting, readout, and emptying. So, this process will go on continuing every time you are trying to read out the state of a qubit. Now, as I discussed with you in the first case, injection case, both your spin up and spin down levels are below Fermi level. So, an electron can tunnel in with random spin, right, but obvious. Now, the electron is trapped inside the dot, this is known as Coulomb blockade. The electron is trapped inside, and the Coulomb blockade prevents another set of electrons entering into the system, right, and this is known as waiting. So, I have an injection and then I have an waiting. What is an injection? Injection basically meaning spin up or spin down levels are all below EF. So, an electron can tunnel through with random spin. Waiting is electron is trapped inside, because of the Coulomb blockade it does not allow any extra electron to enter inside, and it waits there till you do the readout circuitry. When you have a readout circuitry, if the spin is pointing to the top, its energy lies below the Fermi level and stays in the dot. If it is down spin, its energy is above EF and it tunnels through tunnels out, replacing the spin electron. That is what is shown here, the last part. This one is the first part, which is injection. This one is waiting. This one is readout, and this is again emptying, which we have seen. So, there are 4 states which you need to be very careful about as far as the whole process of readout is concerned. And then again, once you have done the readout here, you both levels are pushed above the Fermi level and the dot is cleared again. The dot is cleared again to have the next set of pulse coming into the energy level in that state. Now, let me finalize the whole idea which we did in this lecture. We looked into a cryo-CMOS controller design. We looked into 2 important points. One was APD method by optical detection, and then we looked into SPAD for single photon detection using avalanche photodiode. We looked into linear amplifier, a TDC, and finalizing the digital output. Another methodology was using microwave pulse, within which we were giving pulses which were for emptying, then you are basically waiting, injecting, readout, and then finally again emptying, and the whole process gets repeated. And these are all repetitive process which are controlled by whom? They are controlled by this system here, right. So, who will control it? These will. So, you have therefore a DAC at the input, which converts the digital signal into analog signals, which again drives this demux, and it selects which of the qubits you need to read. So, if you have multiple qubits, the idea of microwave sensing is that it is highly scalable. So, if you have multiple qubits available, you can simultaneously detect the state of the qubit very easily, and that is the advantage of microwave over an optical one to a larger extent, right. With this, I think we will stop here today, and thank you for your patient hearing. Till we meet next time, goodbye.